So crack propagation means, right, the growth of a crack. Fatigue life, you know from your earlier courses, if you are subjecting a component to fatigue loading, then until how many cycles of the fatigue life it can fracture and so on, right? So it is fatigue life. Failure prediction is of course simple, that can we predict when it will fail, right? So this I am attaching with this one. You see, because if you have a normally increasing tensile load like in a tensile test, then that is not real. In the real life, you do not keep on applying load until it fractures. You have designed it for a certain maximum load, and therefore during the life the load generally remains below. You are running your car. All the parts, piston and cylinder, has a cyclic load where the things go up and down, up and down. The shafts and axles and camshaft and so on rotate, so there is a cyclic fatigue loading. But you have designed it in such a way that the maximum load, the load combined with the thermal load, right, is always below the design load. So can you then predict when fracture will happen, even though the load is always below the design load? So that is failure prediction. Stress intensity factor, right? Remember, when you were doing your solid mechanics and especially your machine design, then you even studied stress concentration, that if there is a 90-degree change, then what happens? If in a flat plate there is a round hole, then what happens? And you found the values of how to calculate and so on the stress concentration factor. Now here there is a little more. That was a stress concentration factor. Now it is called a stress intensity factor, because here you are saying that you will study the type of crack that is there, right? The type of crack, it is a straight line, it is round, it is elliptical, how the load is applied and so on. So the crack geometry and the type of loading together will tell us how much stress intensity there is at the near the crack. So this will be called a stress intensity factor, and this will become the beginning, the basis of all my fracture mechanics calculations. Okay? Then we already have talked of this word earlier in the slide just before this, fracture toughness and impact toughness. Toughness, simply toughness, only toughness is the ability of a material to resist fracture. Okay? Toughness is the ability of a material to resist fracture. So the more general toughness is the fracture toughness of the material. We will study during this course how we measure this and so on. How do we define this? Impact toughness is a subcategory of this. Fracture toughness is the general category. Resistance of the material to fracture in any type of situation. But if the load is impact loading, then this toughness is called impact toughness, right? Fracture toughness testing, of course, the general type of fracture toughness, how do you test it? Impact toughness testing, of course, the impact toughness, how do you test it? Plane stress and plane strain are again from your very basic mechanics and basic material science and so on. It simply means, if you remember, this is PLANE, plane, right? XYZ, XY plane, not PLAIN. That PLAIN is simple. Something is simple. This plane is this plane, right? This is a page. This is a flat plane. When do we call it a plane? When it is a 2D problem. Normally everything in reality is X, Y, Z, 3 planes. But if one of these stresses, sigma X, sigma Y, sigma Z, if one of these stresses is very small compared to the other two, then you can neglect the 3D approach and you can treat it as a plane stress problem. Similarly, if one of these strains, gamma X, gamma Y, gamma Z, if one of the strains is negligible compared to the other two, then you study only the significant two. So the strain is supposed to be in one plane. So of course all the mathematics and all the mechanics will become much simpler if a real world case can be treated as a 2D case, and it happens under certain conditions. When we talk a bit later, we will again discuss it. So this was a very big, I have been a little brief in this terminology now because you have already studied it and you have already submitted the homework. And of course, in the next online session, if there is any other clarification that you need, you can always ask me. So now we get back to where we were. We were talking of toughness and impact testing, right? So impact loading, toughness, impact toughness, toughness. We were talking about this, and let us see and try to explain it a little more based on some. This, you know, you have done this in the material science, impact testing machine. Impact testing machine. The engineer scientist who designed this was of a French origin. His name was Charpy, Charpy. So this is also called a Charpy impact testing machine. But it is, you remember that there is a dial here. This could be an analog dial or a digital dial on which this big arm and hammer is there. This is originally in a flat position and you can lock it. And there is a sample like this where there is a very sharp notch, V-shaped notch cut into the sample. So this sample you load here in the sample loader. Once you load here, then you click here and the hammer is dropped. And the hammer is designed in such a way that, of course, now it is an impact load, big impact load, so it will break the piece. Now, because in the machine this load of the hammer is known, the distance through which it travels is known, and after breaking it, where does it stop? What is the maximum position where the hammer goes before coming back? So based on these distances, the potential energy, right? Energy due to position, right? So that is calculated, that is converted into the kinetic energy, and the machine directly gives you the reading of what is the impact toughness of the material in energy units. In energy units, it is called CVN, Charpy V notch energy, and it is in energy units if you remember. So this is a machine. It is already calibrated inside in such a way that the weight of the hammer, the distance through which it travels, and then the distance through which it travels after breaking the piece where it stops, all those go into the calculation and you find the total work done or the total energy spent, whatever you call it, right? So this is impact testing. Charpy impact test, we know it is also known as the Charpy V notch test. Standardized high strain rate impact, right? Widely applied in industry, easy to prepare and conduct results. Test was developed in 1905 by the French scientist Georges Charpy. The standard Charpy test specimen is a bar of metal or any other material, 55 by 10 by 10 millimeter. A V notch is machined across one of the larger dimensions. Its depth is 2 millimeter. There is a 45-degree angle and a 0.25 millimeter radius along the base and so on. So if you are interested, then these are the details of the Charpy impact test. The procedure, of course, is striking a specimen with a hammer on a pendular arm. There are two types of specimens. One is called the Charpy specimen. The other is called an Izod specimen. If you did this test during material science, most probably we had some Izod samples. The only difference is that in the Charpy sample, the notch is towards the hammer, opposite to the hammer, and in Izod it is towards the hammer, right? You have a piece of material where there is a notch cut. So if this notch is facing the hammer, it is one type. If the notch is opposite to the face of the hammer, it is the other type. And we know you can read lines. And here I am showing you again, right, that this is the machine. The machine is the Charpy impact testing machine, and the specimen could be a Charpy specimen where the notch is not facing the hammer, and there is an Izod specimen where the notch is facing the hammer. Of course, this is not the only difference. The difference is that the dimensions of this and this are also slightly different. But if all the different materials that you are testing have Charpy specimens, then you can compare their breaking energy. If all the materials that you are testing have Izod specimens, then you are comparing this. But if you test some on Izod samples and some on Charpy samples, then you cannot really compare which is tougher and which is lower, right? So this gives you energy. This does not give you the real toughness. This gives you the toughness only in the case of a hammer test. But of course, if we know that this material is tougher, then even in a gradually increasing load, this material will be tougher, right? If it is tougher under an impact load, the material will have a higher toughness under a normal increasing load also. Now, the first slides about the Titanic, right? Now let us see what we are showing you here. Here it is the impact toughness, the energy absorbed. If the material can absorb more energy before it fails, it is ductile. And if the material does not absorb too much energy, suddenly fails, it is more brittle. So if the impact energy is low, right, it breaks at low energy in the impact machine, then it is brittle. And if it takes a lot of energy before it breaks, it is ductile. Okay. So now if this is a class of materials, FCC type of metals, you see that it is very high. So it has high impact toughness. So these are generally ductile materials. On the other hand, these type of materials, high strength alloys, their strength is very high. Their yield strength and ultimate strength is high, but they are relatively brittle materials by nature, because you see, in terms of impact toughness, they break at a very low energy. So these materials are strong, but their toughness is low. That is what we told you in the beginning, that this is a very strange dichotomy in nature, that if a material, a metal especially, has a very high strength, then generally its toughness is low. Okay, so these FCC metals are good in strength, but not as high as these. So they are low or medium strength alloys, but their fracture toughness is high. These materials have very high strength, but their fracture toughness is low. Now, some materials, especially some low strength BCC materials, like low carbon steels and some of thermoplastics, they have a varying nature. They don't have a simple nature. You see, these have almost the same nature. They don't change much if you change the temperature. If you have a low temperature, their toughness is this. If you have a very high temperature, their toughness is this. Very little change in the toughness. Similarly here, at low temperature, toughness is here. At high temperature, toughness is here. The difference is very small. But these metals at usual temperatures of room temperature or higher have a very decent high toughness value. But if the temperature goes low, below a certain threshold, then this very high toughness goes to very low. So this is the ductile to brittle transition type of materials. And there is a certain temperature range. For many metals, it is close to the freezing temperature, that when it goes to freezing or below freezing, then this material at room temperature was a very nice ductile material with good toughness. Now it has suddenly become a brittle material, right? So these materials are all one kind. These are good toughness. These are low toughness. These are ductile. These are brittle. These materials are ductile and brittle depending on the temperature at which you are applying the load. So the ductile to brittle transition happens, and therefore once they become brittle, they can still take a lot of load if it is a regular load, but if it is an impact load, it is a hammer load, and now they have become brittle, then they will easily fracture. So that is what I was trying to explain here. This is already explained to you, but we will talk about a little more, of course, as we always do.